Welcome back, everybody. In this video, we're starting chapter 5, which is about discrete probability distributions. And as always, first thing we'll do is go through and see what we're getting into, take a quick overview of the chapter, and then we'll actually get started. So the chapter here is, as I said, on discrete probability distributions. There's a total of 3 sections in the chapter. If you look in the table of contents, you'll see that both chapter 5 and chapter 6 are on probability distributions. Chapter 5 is on discrete. Chapter 6 is on continuous distributions. Basically, backing up a little bit, what a probability distribution is, you can kind of think of it as being like a function, like from algebra, a function where it takes as input some outcome to a procedure and gives the as output the probability of occurrence of that particular outcome. And the difference between a discrete and a continuous distribution is just whether or not what you're looking at has a discrete number of possible outcomes, that is something that's counted, or if it's continuous, like something that is measured, okay, like a time or a length. So that's the big difference between chapters 5 and 6. Chapter 5 just deals with discrete things, so things that can be counted rather than measured. There are a total of 3 sections in the chapter. The first one is on it just says probability distributions, and that's the usual kind of introductory section that describes what's a probability distribution, new definitions, terminology, and some examples. Once we have a handle on what a probability distribution is, then we look at 2 particular kinds in sections 5.2 and 5.3. 5.2 are about a specific kind called binomial probability distributions. And then 5.3 is another one, which is about Poisson distribution. So we can't really say more about that until we know what a probability distribution is in general. So let's just go ahead and get started with 5.1. All right, so this all deals with a random variable. So that's where we'll start. A random variable is a variable, and you all know what a variable is from your earlier math classes. And these are typically represented by x, that has a single numerical value determined by chance, that's the random part, for each outcome of a procedure. Okay, so as an example, and then I'll come back to the other definition here in a second. Suppose that we toss a pair of coins. And as you recall, in this class, all of our coins are assumed fair unless you're told otherwise. We're going to toss 2 coins. Let x represent the number of tails that we get. Then x is a random variable. So the random variable is numeric. So in this case, we're defining it to be numeric, the number of tails that you obtain when you toss this coin. So a probability distribution is a description that gives the probability for each value of the random variable. It's often expressed using a table, formula, or a graph. So to see an example, let's go back to our set of 2 coins and think about what's possible. We have 2 coins. The first coin could come out either heads or tails. And then we're assuming that these are independent, right? So for the second coin, the outcomes are either heads or tails, independent of how the first coin comes out. So as far as the number of tails that we get, if it comes out heads and heads, we would get no tails. If it's heads and tails, we'd get 1. If it's tails then heads, we would get 1. And if it's tails then tails, we'd get 2. Okay, so then there's 4 possible outcomes. The chance of us getting no tails is 1 in 4. The chance of us getting 1 tail is 2 out of 4, or 1/2. And the chance of us getting 2 tails is, again, 1 out of 4. Okay, so that's an example of a probability distribution just given by a table. And then, of course, if we wish, we could give a little graphic of this, and a lot of people like to do that. We could cross the horizontal axis, show values of the random variable, which is either 0, 1, or 2, and then the corresponding probabilities. So there's 1, there's 1/2. So we saw that for both 0 and 2, the probability is 1/4. And then for 1, it is 1/2. Okay, so there's a little histogram essentially that shows the values of our random variable. Okay. Moving on. we have discrete and continuous random variables, as I'd said. This chapter focuses on discrete variables. We want to make sure that we can tell the difference between the two. So in this example here, it says, let X represent the number of calls that a salesperson makes in a day. Then X is a discrete random variable. It's discrete, it's something that can be counted. Does a salesperson call 3 clients? Do they call 10 clients, 2 clients, or no clients? It's going to be some number that you can count on your fingers. That makes it discrete. Okay, contrast that with the second one. Let X represent the number of hours, including parts, that a salesperson spends on the phone each day. In this case, it's hours, which is time, and it can be measured. X is a continuous random variable. We could say that a salesperson spent 2.868 hours on the phone one day, and our precision there is only limited by how good our clock is, right? We could extend our measurement as far as we have the technology to do. And that's different from the prior example where we were just counting possible outcomes. So what we've got so far is, just backing up a little bit, what we've got so far is what a probability distribution is basically kind of like a function, where the input is going to be some random occurrence, and the output is some numerical variable that is a function of all the different possible outcomes of that random event. Okay. Okay, so more detail on the discrete versus continuous. A discrete random variable has a collection of values that is finite or countable. Okay, if there are infinitely many values, the number of values is countable if it is possible to count them individually, such as the number of tosses of a coin before getting tails. So these two descriptions, by the way, are taken from our textbook, and I find them kind of, for most students, they come across confusing, which is why I can recommend thinking of it instead of the way the book is describing it. Think in terms of a discrete variable is one that you would count, and a continuous variable is one that you would measure. And that you will get the right understanding thinking of it that way, because we really don't go into countably infinite versus uncountably infinite in this course. So discrete variables, and that's what we're looking at in this chapter, chapter 5, are things that you can count. Continuous random variables, stuff that you can measure, that is dealt with in chapter 6. Okay. Some requirements that a distribution has to have in order to be a probability distribution. So there's 3 different requirements. So let's look at each of these. So first thing, there has to be a numerical random variable x, like our number of tails in our first example, and its values are associated with corresponding probabilities, right? So our variable has to be numeric, and the values are associated with probabilities. As we know, probabilities, let me skip over 2 for a second. Probabilities all lie between 0 and 1, right? You remember that from chapter 4. So every possible value of our P of X, our distribution, has to be between 0 and 1 for every value of X. Okay, probabilities are always being between 0 and 1. Okay, the other thing is that the sum of the probabilities has to be 1. And if you think about it, the reason for that comes kind of from our OR formula for probability. If something has to happen, right, for whatever random task we're doing, something is going to happen. When we toss the 2 coins, let's go back to our coins for a second. When we toss the 2 coins, we're going to get one of these outcomes, right? There will either be 0, 1, or 2 tails. There are no other possibilities, but you're going to get one of those for sure. And so since you're going to get one of those for sure, it's something that is definite or certain, and so it has probability 1. And so you're going to get one of these possible outcomes with probability 1. And then, as you know, 1/4 plus 1/2 plus 1/4 is equal to 1, right? That's what this is saying, is that all of the probabilities in the distribution have to add up to 1. You might get values that are near 1 just because the data values in our table were rounded a little bit. Okay, so an example. This one's taken from the book. Here it says groups of people aged 15 to 65 are randomly selected and arranged in groups of 6. The random variable x is the number of people in the group who say that family and or partner contribute most to their happiness, and then they give the source. So a couple things go with this. One is in the first entry in the table, there's a 0 with a plus sign, and I wanted to mention what that is about. Here, the values in the table are rounded to the thousandths place, 3 digits behind the decimal point. The p of x for 0, an x value of 0, is so small that if we wrote it out as a decimal, it's 0.000 and then something. If you round it to 3 decimal places, it's going to look like 0. So what they do is they put 0 with a plus sign here to say, okay, well, it's not 0, but it's so small that if we rounded it like everything else in the table, we would get a value that looks like 0. So that's what the little plus sign there means, is it's a number that is so small that it looks like 0 when you round to this extent, but it isn't actually probability 0. Okay, so then second thing is we want to make sure we understand what's going on in the table. We have a group of people, a bunch of people between ages 15 and 65. We've put them into groups of 6. Okay, picture there being like some big room that has round tables in it and 6 people sitting at each table. Okay, so there's 6 people at each table. You go to each table and ask the people there, okay, for how many of you is it true that your partner or your family contributes most to your happiness? Or is it your car or your job or your dog or something? Okay, is it your family or is it something else? The number of people who say that it's the family or their partner is could be nobody, or it could be all 6 people, or maybe 3 people at the table tell that's true. So the probability that you go to a table and 4 people say that it's their family, that probability is going to be 0.279. So out of all the different tables of 6 people, what is the probability that X people give family as the most important thing for their happiness? That's what this probability is measuring. Okay, so as far as answering the question, we're just to decide if this thing is going to represent a probability distribution. So let's check everything, all the requirements. So the first requirement is, yes, there's a numerical random variable. It's random because there's nothing in there about how the people are seated. There's no organization. People are not sat with their family necessarily, anything like that. So it's random. And the values are associated with probabilities. So we have probability sitting here. We should check and make sure that all of those p of x's add up to 1. So let me start there. So we have 0.003 plus 0.025 plus, and so on, up to 0.208. Okay, so let me go ahead and add those up for us. All right, so adding up those rows for 1 through 6, it ended up being 0.999 for the probability. And for the first one, it was so low that it gets rounded to 0. So I think that's pretty convincing that the total of all those probabilities is going to end up equaling 1. Finally, for the last criterion, each of these probabilities is between 0 and 1. So the third requirement fits as well. So yes, we could say it's a probability distribution. Okay. All right, another example, try that again. Here it says, Ted is not particularly creative. He uses this pickup line. If I could rearrange the alphabet, I would put you and I together. Okay, the random variable x is the number of girls, hopefully women. I guess he could be a kid, but the number of girls Ted approaches before encountering one who reacts positively. So this is our values. It looks like all of the numbers are between 0 and 1. We do have a random variable x between 1 and 5. We should probably check and see if those p of x's add up to 1. So let's do that. Okay, so let's see what we get for all those. Right, so adding up those values, I got 0.601, and that's not 1, obviously. And so this one is not a probability distribution because the probabilities would have to all add up to 1. Okay, one more. So at this point, you can pause the video, try this yourself, decide if this thing is a probability distribution, and then resume the video and see how you did. All right, so I'm going to assume you did that. So here we have a random variable x. There's no story that goes with this, so we're just going to assume that this is a random variable, numbers 0 through 3. And then there's probabilities associated with that. Each one is between 0 and 1, so it looks like the main thing is to make sure that they add up to 1. And sure enough, they do. Sorry about that. All right, so yes, it ended up being a probability distribution. All those probabilities added up to 1. Okay, here's another example. A sociologist surveyed the households in a small town. So a sociologist goes door to door, surveys all these households. The random variable x represents the number of dependent children in the households. We're to determine the probability distribution's missing value. So what's different on this is we're not trying to decide if this thing is a probability distribution. Instead, we're told that it is, and we need to figure out what the missing value has to be. So each of the p of x's is between 0 and 1, and we know that if this thing is a probability distribution, the sum of the p of x's will have to be 1. And so we should see what the probabilities are that we've got so far. So 0.07 plus 0.20 plus the others that we have here, 0.13, let's see what those add up to. And then take away from 1. What's missing is 0.22. That was the missing value. Okay. Again, this is just to reinforce the idea that all the probabilities have to be between 0 and 1, and they all have to add up to 1. Okay. A probability distribution has a mean and standard deviation. So that's what's next. So there's a formula for it. There's formulas for everything, right? So the formula for the mean of a distribution goes like this. It's mu. It's going to be the population mean, not an x bar. And the reason for that is that it's mu instead of x bar is that we have every possibility, right? Every possible value of x, that's a population. So we have all those values. So it's a mu. It's the sum of x, p of x. So each possible outcome multiplied by its probability. Let's try one. Okay, a pair of coins is tossed. Let x represent the number of tails. We know that x is a random variable. So this was our first example from earlier. The probability of us getting no tails was 1/4. The probability of us getting 1 tail was 1/2. And then the probability of us getting 2 tails was 1/4. So then if we wanted to find the mean, it's going to be 0 times 1/4 plus 1 times 1/2 plus 2 times 1/4. Okay, so that will be 0 plus 1/2 plus 1/2, which is 1. Okay, so what does that mean? It means that if you toss 2 coins, you're going to get 2 tails sometimes. You might get no tails, you might get 1 tail. On average, over the long term, if you do it a lot of times, you're going to get an average of 1 tail. Okay, variance and standard deviation. Variance is the square of the standard deviation, okay? So we just got the formula for variance here. We'll take the square root to get the standard deviation. In fact, let me just go ahead and put that down here now. The standard deviation would be the square root of this sum of x minus mu squared times p of x. Okay, so reading the formula from the inside out, you take the deviation from the mean, just like we'd had way earlier, difference of an x value, which is an outcome, from the mean, square those to turn them positive, and then each is multiplied by the probability. And then you add them all up. And then finally, we would take the square root at the end to fix up the units. If you look at this really carefully, we're multiplying a probability times a squared deviation, which is basically the mean of the deviations. Okay, so let's try it. Okay, so back to our pair of coins again. X is the number of tails. We've got our random variable here. We want to get the standard deviation. Okay, there's two different formulas for the variance and standard deviation. They're equivalent algebraically. The first one I think is easier to understand. Deviation from the mean, you square them, multiply them by the probability, and then add them up. The second one can be easier to calculate with if you're doing the calculations by hand. And so what you do is you square the random variable, multiply by its probability, you add up all those, and then subtract the mean. That one turns out a little easier to work with, so we're going to go ahead and use that one here. So x squared p of x for each of these. So let me go ahead and make a column in my table for x squared. X squared 0, 1, and 4. Let me make a column for x squared p of x now. X squared p of x, that will be 0, and then 1/2, and then 1. Okay, I'm multiplying the x squared column by the p of x column. And then we wanted to add that up. Okay, so that is 3/2, right? 1/2 plus 1 is 3/2. And then we're going to subtract the mean squared, right? In this example, we determined that the mean was 1. Okay, so we'll have 1.5 minus 1 squared. I'm just putting the squared on there so you know that I didn't forget it. 1 squared, of course, is 1. 1.5 minus 1 is 0.5. And so this will be the variance that we got using this second formula. To get the standard deviation, we'll just take the square root of that variance. And so that will be 0.7071 just about. We'll just round that to 0.71. All right, so this has been a quick example of how you can find the mean and standard deviation for a discrete distribution. The formulas, you should get used to those, maybe write them down in a convenient place so that you have access to them. The mean, easier for me at least to remember, multiply each outcome by its probability and add them all up. For the variance, the computing formula is a little bit easier to work with, although maybe not as easy to remember. This one, you take all of the outcomes squared times their probabilities, add them up, and then take away the square of the mean. All right, that takes us to the end of this first part on 5.1. In the next video, we'll continue with 5.1 with some more examples. In the meantime, let me know if you have any questions, and then have a